Let me start. So first of all, I would like to thank Joel for inviting me to give this two lectures on tensor networks, algorithms, and applications. These lectures will mostly be related to how we can use tensor networks to study, say, for example, spin models, Ising model, classical XY model. These will be the models which we'll discuss during the course of two lectures. And I'll try to tell you why this method is so effective in lower dimension, at least 1 and 2 dimensions, as compared to more traditional methods which you might have heard in other lectures like Monte Carlo uh, methods. So this lecture will be hands-on. So I guess most of you have access to some Google account because we'll be using something called Google Colab, in which you can write codes and run them in real time without about the packages and other things. I also assume that you have access to the Dropbox folder, and you can see there's a folder called uh, by my name, in which you have some files, and we'll be using those files. If you don't have those access to those Dropbox folder, just let me know and I'll send an email to all of you. Okay, what do I want to talk about? I'll start to talk about this tensor network approach to many body systems and also QFTs if we get time uh, at the end of the second lecture. We won't be able to reach QFTs for sure in the first lecture, but probably by end of second lecture we have some time. Okay, so we'll start by looking at some methods of exactly diagonalizing the Hamiltonian, for example, for Ising model for a small number of spins. And then we'll go to the basics of tensor networks. After going through the basics of tensor networks, I'll discuss a 2D classical Ising model and compare to the exact result which we know very well from work by Onsager and many other people. So we'll see how tensor network methods, numerical, help us to get to the exact result and uh, what are the things we have to do in process. Then I'll discuss 2D classical Ising model, 2D classical XY model. And then, depending on how much time we have, I'll discuss some other uh, some gauge theories. And also, if we get time, we'll come to entanglement entropy, and we'll discuss 2D Ising model with magnetic field. So, for example, this Ising model was when H is, so we might discuss H not equal to 0 if we have time. Okay. So some additional remarks. As I already mentioned, these will be hands-on lectures and the flow will be determined accordingly, hopefully. Uh, you will have to participate and do the coding exercises because I think it's important that at the end of two lectures we learn something, and most of you can try to attempt to code even after these lectures so that you become self-proficient in tensor networks coding at least. So we have to do that as we go along. So you have to participate and do it on your laptop and PC. We need internet and Google account. So let's start to talk about the basic idea about tensor networks. What is the problem and what do we want to do with it? So for example, when we talk about a spin half particle, the Hilbert space has dimension 2. It can be spin up and spin down or spin down. When you take n such spins, the Hilbert space has dimensionality which is given by 2 to the n. Now consider a spin chain or say spins which are oriented in a line, and there are 30 of them. The dimension of such a Hilbert space, if you want to store the state of the entire system, the dimension will be 2 to the 30. You can write 2 to the 30 as like this, 2 to the 10 is to 3, and 2 to the 10 is roughly equal to 1000. So this 2 to the 30 is roughly 10 to the 9, right? And this is impossible to fit in any modern day computer. If you want to take, if you want to understand, say, for example, the quantum state of 30 spins, you have to store this Hilbert space dimensionality, and it is impossible to do with current day computer. So then the thing we have to ask ourselves is, how are we going to understand anything about, say, for example, the ground state properties of spin models, if we cannot do any kind of numerical on modern day computer? It turns out that the nature is kind in some aspects, and we don't have to deal with the entire Hilbert space when we want to study, say, for example, the ground state of the Ising model. If we want to calculate the, say, for example, energy of Ising model in quantum Ising model in a magnetic field, you don't have to worry about the entire Hilbert space. So the main message here is we don't need to work with the entire Hilbert space, since for most of the cases which will be interesting to us, nature lurks in a small corner of the full space. So the physics is concentrated in a very small region of that huge Hilbert space, which we just uh, discussed about. And we'll see this in detail later. Before going to those details, I want to talk about the notion of gapped and gapless systems. So when I mean uh, gapped system, I mean that delta E is not equal to 0, as you can see here. But what is delta E? Delta E is defined as the minimum of this part minus the ground state energy. What is this part? This part is the energy of a state. You compute the expectation value of the Hamiltonian operator for size, where the psi is not belonging to, is belonging to a Hilbert space, which does not comprise of the ground state. So you take all the states which are not part of the ground state and then compute this. So and then you subtract the ground state energy. And in thermodynamic limit, if you find that delta E is equal to 0, then we have what we call as gapless or critical model. If delta E is not 0, then we have a gapped system, right? So these are two different systems which we talked about when we try to understand the tensor network formulations of spin model or other uh, quantum field theories. Now, gapless models where delta E is equal to 0 are captured in field theory language by a special class of QFTs, which are known as conformal field theories. So conformal field theories are defined, can be used to describe these spin models, which are gapless models in the sense that there is no delta E is equal to 0. But for what will follow in this lecture for now, we'll restrict to gapped systems rather than gapless system. We can also deal with gapless systems using tensor networks, but that is a little more sophisticated, uh, and we won't probably have time to go into those details. But there is certainly tensor networks formulation for both gapped and gapless systems, at least in lower dimensions. Now, I just mentioned that we don't have to worry about the entire Hilbert space, but the interesting physics is only concentrated in a narrow region of the Hilbert space. So, what is the criteria? What is the how do we really identify which corner of the Hilbert is actually preferred for gapped systems? The answer to that is given by entanglement entropy. So, for example, if entanglement entropy is scaling in some certain way, then we know that state is important to understand the ground state of this gapped system. If the entropy is scaling in some different way, then we don't bother about that, because that is not going to play in the description of the ground state of the system which we want to look into, right? So entanglement entropy is very important because it tells you what region of Hilbert space is actually contributing to the, say for ground state of some local Hamiltonian which we have. Okay. So this is the cartoon which you'll see at various places if you go into this tensor network literature. So for example, if we consider a local gapped Hamiltonian, for purposes of this lecture, local gapped Hamiltonian, I already understand what gapped means. With local, I just mean that, for example, when I consider a Ising model, they're just next to neighbor interactions, right? So you don't have interaction which extend over several lattice sites, or for example, spin 1 won't be talking to spin 10 or so on. So these are all local gapped Hamiltonian with short range interactions. And then the entire Hilbert space, as I already mentioned, is given by 2 to the n. But the interesting physics is happening up here, which is a very small, tiny corner of a Hilbert space, which are known as area law states. Right? So, for example, the entire if you take any generic state in this Hilbert space, you'll see that it scales like volume. So, if you compute the entanglement entropy, you don't need to know. We'll discuss later if we have time what entanglement entropy is and how we calculate it. But just for now, we just need to understand that there is some quantity which is called entanglement entropy, which, if scales like volume, belongs to this part, and if it scales like area, belongs to that small blue dot you see. If it belongs to that blue dot, it's known as area law states because the entanglement entropy goes like area of that region. This is also known as area law of entanglement. If it is a generic state which has no role in the ground state properties and so on, it will scale like volume and is known as volume states, right? Okay, so now we should try to understand and try to do some small coding. So the first thing I'll want to do here is I'll just open my, just a second. Minimize this, not cut this. So this, I kindly request all of you to go to this Google Colab on your computer. Let's see. Okay, there are some questions here. Let me go back to them and see. Can you maybe brief my using stand? Can you briefly explain why you use entanglement entropy instead of omega key entropy? I don't know what omega key entropy is. We use the entanglement entropy, which is known as the von Neumann entropy, which is based on the method of partial traces. And that is what we use to determine which states contribute. So I can talk about that briefly in second lecture, but I don't know what omega key entropy is, sorry. I know von Neumann, Renyi entropy. These are the entropies which we use. Will these exercises work on Jupiter as well? Yes, that is, these exercises should work on Jupiter as well, but I'll be using this Google Colab. So for now, let's just focus on this collab. So we can just name this, say something like exercise 1. And we want to compute, do exact diagonalization. For this exercise, you don't need to download any files from the Dropbox folder. So you can just follow what I'm doing here, and then we'll see what happens. For the other exercises, however, we need to look into the Dropbox folder. So you should download the files which are already there. Okay, so let's. You should try to do this on your laptop as we go along, and I'll keep on explaining. So we want to plot for example, the ground state energy after exact dilatation. So we are doing this matplotlib. We might need some linear algebra, so we'll just also import that just to be completely. And I like to import this sys because it tells me about some error messages and will exit the code if certain conditions are uh, not satisfied. Okay, so this is the basic framework. Now what we need to do is we want to look into the Hamiltonian, right? So let's see. So let's look at this Hamiltonian which we have here. We have to consider this Hamiltonian of 3 spins. We are only looking at 3 spins right now. 3 spin quantum easing model, and the Hamiltonian is given by sigma x of location 1 product with sigma 2 at sigma x at location 2, and then 2 and 3, and then 3 and 1. So this is periodic boundary condition. So you have 3 spins is connected to the first one. And then we have this magnetic field term, which is given by H, sigma 1z, sigma 2z, and sigma 3z. Now, since n is equal to 3, the Hamiltonian operator, we'll write it in a form of a matrix. And for 8 by 8 matrix, we can just use exact diagonalization without worrying about any tensor networks and compute the ground state energy for various H, right? So that is what we'll try to do. Now, if this n was, say, something like greater than 10, then we won't be able to do that. And at some point, say n equal to 20 or 22, you just cannot do it because your computer will run out of memory and you won't be able to store that size of a matrix and diagonalize it, right? So we'll work with n equal to 3 at the moment. Okay, so let's go back to this collab, which so, I'm assuming all of you have collab right now. If you don't have collab, just write in the chat that you don't have it, and then you can just follow it. But I assume most of you have this. This is very helpful. Okay, yeah, you can do Jupyter. It should be fine. Okay, so collab is just mm, uh, it's just uh, like a website maintained by Google for doing these kind of collaboratory research where you code and do computations and so on. So if you just write Google Colab on Google and open it, you'll come to something, and then you open some new notebook and you will have something like this. Okay, so there are some questions. Just see. Yeah, Jupyter should be fine. You can do it on your local computer. It's not important how you do it. I'm more concerned about the physics which you are going to do, and that will be the same. So that is what we'll be using. Okay. So after calling these initial mm, things which we need, let's just define some more useful uh, stuffs which we will require. So E is just an identity matrix, 2 by 2 identity matrix. Double E is identity matrix of size 4 by 4, as we'll see later on. And then I defined something called X, which is polymatrices, poly sigma X, which is just given by this. So this is sigma X. and we'll have to do sigma z, which is 1 0 0 minus 1. Now we'll need a product of two sigma z, which we can call sigma x, which we can call, so this is called z, which we can, so np cron just takes a Kronecker product of two matrices. So for example, when I do np cron x and x, it will take, so this just means sigma x tensor product with sigma x. So this is xx, and now I can define Hamiltonian part of this, and that is just np dot cron xx comma e plus e comma xx plus p cron of x ex. Okay, so let's just see if we are doing it right. And picron xxe. So this is sigma x identity sigma x. So this term here is sigma 1 x cross sigma 2x, and then I stick in identity matrix at the end, and this is identity times sigma x. So location 2 and 3. So this is at site 1 and site 2. This is at site 2 and site 3. And this is at site 3 and site 1. So you see that the third and the first elements are x. The middle one is identity. So this is hxx. Now the Hamiltonian also has another part, and that we can call hz, and that is given by z comma e plus np cron e comma z comma e plus same thing inverted. So this is my hz. Let's just see if it is correct. np cron z e z e e is z. Okay. So this is all fine. If there is anything which is not clear till now, you should ask in the chat box. Otherwise, we'll keep moving forward.
I just want to say mine didn't compile the XX successfully. It says I can't multiply sequence by non-int of type list. As far as I can tell, my code is absolutely identical.
No, it should work.
Adam, can you just copy and paste me your code if you don't mind?
Sorry. Oh, okay. This one.
I was just asking Adam. Yeah.
Okay. Yeah. Okay, so if omega k is the quantum relative entropy, it is related in some to the entanglement entropy, but that is not what we look when we try to. ADL law of states mostly apply for the von Neumann entropy, which is the Renyi entropy, and when you take the limit n to 1, right? Okay, so let's just wait for everyone to be on the same page. So right now we have this Hamiltonian written down already, which is hz. Okay, so I'll just keep moving forward. If there is a problem, we can come back to later. Now I want to do this for multiple magnetic fields. So I'll just introduce this n steps, which is like yeah. So I introduce H, which is equal to NP arrange, say, magnetic field 0.0 to magnetic field 2.0 in steps of 0.2, and we'll do list. We'll add this to a list, and then n steps will just be, number of steps will be given by NP shape of H, and reading out the zeroth element. Okay. So now we'll generate different values of H, and then the number of steps will just be the shape of that uh, list we generated. And now we should also store the ground state energy for each of these n steps. So we'll do that. Okay. So this is the basic feature which we have. Now we can do for I in range 0 to n steps, and we can do H is equal to hxx, as we saw in the description of the problem. Hxx plus hi times hz, right? So this is the total Hamiltonian now. What do? We use LA linear algebra package, which diagonalizes the matrix H and throws eigenvalues and the eigenvectors. We need to use eigenvalues, which is the ground state energy, and that should be the minimum of D, right? So we'll take this Hamiltonian, which is 8 by 8. We'll then diagonalize it, and then we'll take the lowest eigenvalue, which is given by min of D, right? So this is the ground state energy or the lowest eigenvalue. Okay, so this is fine. We can do PLT dot plot. We can do E H naught. We can set a marker here. We can put some title if we want. Maybe that can be done later on. PLT dot show. Right. So this is what we have, and now we'll try to run this and see if there is any error or whatever. Otherwise, we'll get the answer. It's running. Okay, so it throws an error. E naught is not defined. Oh, okay, so E naught is different. No. Wait. Okay, now it should be fine. Okay. So we did this, and now we have a plot of magnetic field on the x-axis. As we can see, it goes from 0 to 1.75. We have the ground state energy, which, as you can see, depends strongly on the magnetic field, and this is the plot which we get, right? So this is 3-spin quantum Ising model by exact diagonalization, right? Now, if there is any question about this, I can take that. Otherwise, I'll go now to generalize this to n spins, not necessarily 3. So we have now solved the problem for n equal to 3, but now we have to go and solve this for any number of spins n. Even we can solve it, as I already mentioned, for spins greater than, say, 15 or 20, depending on how much memory we have, right? Okay, so yes, can you explain what this plot is showing us a bit more? Yeah, this plot is showing you the variation of the ground state energy. So if you compute the ground state energy of quantum Ising model for 3 spins, note that 3 spin is not the thermodynamic limit. It's like very trivial. N equal to 3 has no, it's just 3 spins. If you calculate the energy of 3 spins with some magnetic field, this is the value you get. So you get, say, for example, something close to -1 for no magnetic field, and you get something like 1 point uh, for magnetic field h equal to 1, you get something like -3.5 and so on, right? So this plot is just showing us how, yes, it has periodic boundary conditions. Uh, uh, so this plot is showing us the energy variation with H for periodic boundary condition 3-spin quantum Ising model. Okay. So are there more questions here? Okay. If not, I will try to go back to my iPad here and then talk about the next thing we have to do. Now, the next thing we should do is we have to generalize this to n spins, right? And then once we generalize this for n spins, a good check is that we produce the results for n equal to 3, which we just did. And then we'll try it for some n is less than 10. For 10, the dimension is 1024. Okay, so we'll do it for some n. Yes, this is one-dimensional quantum Ising model. I'll talk about the two-dimensional classical Ising model later on. This is just a 3-spin quantum Ising model right now. I'll talk about the thermodynamic limit of two-dimensional classical Ising model later on in the lecture. Yeah, thanks, Joe. Okay, and just to be sure, using all the sigma x matrices and such is just to generate the Hamiltonian with the proper +1 and -1 for the Ising model. Yeah, that's correct. So we write down the Hamiltonian in terms of sigma x so that we have the right Hamiltonian which we then diagonalize. Okay, so let's move now and try to generalize this to n spins. How are we going to do that? So to generalize this to n spins, I think the thing which we should do is we should just write down a function which we can call, say, build h, and we'll give that function two inputs. One is the number of spins which we want to look at, and the second is the magnetic field. Let's write some condition that if n is greater than 10, it will not, it will just exit. Okay, so this is just a condition that I don't want to deal with n equal greater than 10 because it will take too much time. Probably it will crash. Uh, and so this is condition will ensure that. And then now it isn't immediately obvious why the tensor products being in that cyclic order. Yeah, okay. Yeah, let me just finish this and then I can read them. Till then you can think about the problem, think about it a little more. Okay, so let's see. I have to do HZ. The way I like to, there are different ways of doing this, but the simplest way which I found, like, came across was something. Okay, this is Z, should be Z. So I'll start from the basic n equal to 3 and then go to some number of spins n, whatever we want to take that n as. And h axis is p cron. P cron I 2 to the -2. This is XX. H given by NP cron HZ is E plus NP cron. We'll just copy this thing here, put it here. And then once we are done with this, hxx will just be equal to hxx plus np cron x comma np cron. As you can see that writing it for a general n is little tricky, but we'll check that it reproduces the result which we know for okay. So hxx is this hxx. Now h is h just hxx plus h times hz. Okay, so now this function has to return me h, and then instead of this line here, I will just have h is equal to build h say 3 comma h I. Okay, so let's see. Okay, now this is fine. It's fine. So let me just print e0 some 3 or something like that. Okay, so we write down some function which we call build h. And let me just show you first that for n equal to 3, both of them give the same answer, right? If both of them are giving the same answer for n equal to 3, we know as a check that what we have written in the function is correct. So let me just run this with the build h function and see what I get. Okay, what is the error? Let's see, I get du LA, I get minimum of this return h. There's an error. Okay, I'm coupling x operators at different spin sites. Let's see. hxx comma e2 to nxx cx. Oh, I see. Okay. Yeah, I don't know why this is not working. Actually, you know what? Let's see. I should have this already somewhere lying. We'll just use that. See. Okay, so let's just print C E05 and see what we get. If we just use the function, we get 3.46 something, which you can just type here. And then instead of the function, now we'll use the original method which we used and see if that gives the same answer. So it gives the same answer. That tells me that the function which I have written down is correct because it is giving me the answer which I got when I was just doing n equal to 3 by hand. So now let's just go back and see the function. It takes two inputs, n and h, and then we construct the same hxx as xx and hz as the canonical product of z versus the identity matrices of appropriate size, right? And now, since we want to do for n spins, we have this for loop which goes from 3 to n plus 1. So the maximum value of n will be capital N, and then this is HXX and this is HZ. You can convince yourself that this is correct because if you put n equal to 3, then you get 2 to the power 3 minus 2, which is 1. So 2 to the power 1. So this is just I identity matrix of size 2 with XX and plus this term. And that was exactly the same thing which we created, right, for n equal to 3 spins. So this is the correct generalization to n spins. Uh, this notebook will be available after the lecture, so you can just go back and work on this. I'll put this in the Dropbox folder. But the basic idea is that this works for any general n. So now if this works for any general n, let's just try to run this for, say, 8 spin uh, easing model for different values of the magnetic field. So I do this, and this is what I get. As you can, so this is for 8 spins. It starts at -8, and then it has some shape, and it varies with magnetic field H, uh, like this, right? So I can also, if 8 was so pretty fast, we can try and see how much time that takes. It'll take some time, uh, but it does show the answer. And this is for uh, for 10 spins. How does it scale with n? Yeah, I have not checked the timings of scaling with n. More so, mm, it's a memory issue, I think. For example, if you have some 4 GB of, like, depending on how much memory you have, it might just, say, for example, if I put n equal to 15 here, the collab might just say that you have run out of cache or something like that. Exactly. So I can try to see, that's exactly what it gives me. So if I do, okay, so no, it gives me an error because of this, but it's just, if I just ignore that and try to run with n equal to 15, it might take a long time, but it might give me an error that it has run out of memory. Basic idea is that it's not practical to do for, yeah, it's NQ for the eigensolver, but I think Joel, yeah, I don't, I should not say anything. I don't know the exact scaling with n. There's there are two different kind of scaling. One is the memory scaling. In these tensor networks, you have the scaling with the bond dimension, which I'll come to later on, and then there's a scaling with n. So I encourage you to play around with the scalings of n. I didn't do that. That could also have been done here, but yeah, this is just a pedagogical exercise. No one does this because it's not practical. It's like you cannot do any reasonable physics because this is not the thermodynamic limit. So we'll come back to this later on. But yeah, the n, it really grows very quickly with n, as we know all these things. 2 to the power 15. Okay, so this, right? So this was the basic Hamiltonian which we had. We tried to solve for 3 spins, and then we generalized this to n spins, right? Okay, so if there are any fundamental questions which I missed, let me just go back. Okay, yeah, I think I should continue. So this was the first exercise. Now we should try to see what do we do now. Now I'll tell you about this tensor notation. So now we have done what we wanted to do about exact diagonalization, and now we won't have to do it again. And we'll try to come up with some more efficient methods of computing the ground state properties, compute free energies. Say, for example, the derivatives of the free energy. How do we do that? Uh, the basic idea is that in tensor notation, everything can be represented by these diagrams, which these diagrams apparently goes back to work of Penrose in the 60s and the 70s. He introduced these diagrams. So for example, a scalar has no legs, so just a blob. This is a scalar. If you have two legs, for example, this and this, Then you have a rank 2 tensor. A vector is represented like this, just one leg. If you have a diagram like this is just matrix multiplication. So for example, this up here is how I am going to represent matrix multiplication. That's because this is AIK and BKJ. So the internal index, which is here, is summed over, right? So K is the index which is summed over. And this gives me some result which is equal to Cij. Now, there can be more complicated tensor networks such as this, in which you have A, B, C, and D. Now, how do we organize the indices on this? We'll use the notation that we start with in the clockwise direction, and we'll start at 12 o'clock. If we write A has indices I, J, and K. So this is I, J, K. And then B has P, Q, I. So this is P, Q, I, P, Q, I, three indices. Then C is another rank 3 tensor. So we have P, M, N, because we are going like this clockwise. And D is a rank 4 tensor, and that is given by K, Q. Q is this big leg, M, N, alpha. So, for example, each of the edges or each of these legs, as I will call them often, are represented by these indices, and then I order the indices like this. So, this is a tensor network consisting of four different kind of tensors, out of which three are rank 3 and one is rank 4. Need to be same here too, I think. N and J. No, N and J need not be same because they are not contracted together. You see, they are free. So if they are loose, then you don't contract. There's only one index in this which is shared by two tensor, which is this Q tensor. Q. This edge, this long edge Q is this one which is shared, right? Okay. So this will become more clear as we go along. This is the basic tensor network notation which we're going to use in this lectures. Uh, okay, so let me just go a step forward. Now, how do we implement this in Python? How do we want to, if you want to do something in Python and want to contract these tensor networks, how do we want to, how can we do this? So we'll do the usual thing, which we all know, import numpy as np or whatever you want, you can call, give it whatever name you like. I import this as np. And then there's a very nice routine in numpy, which is called einsum, which stands for Einstein summation. And then einsum has some specific notation, or uh, you have to write the indices in a proper manner. So there's this apostrophe, and then you have the indices I, J, J, K. So A, I, J, B, J, K gives me C, I, K. So this is the contraction pattern. The first is the first input, which is A, I, J. B is B, J, K, and this gives me some tensor C. So I can just write in Python, C is equal to this thing, and it'll throw me a matrix, which is just the product of A and B matrices, right? Okay, so now we come to our second exercise. So we'll now calculate the trace of product of four random 3 by 3 matrices using einsum and check that result agrees with that obtained from np.trace. np.trace is just a routine which computes the trace, and np.dot, which multiplies two matrices. There are different ways of multiplying matrices in NumPy. You can use the something called np.matmove dot dot, so on. You can construct random matrices using, for example, if I want to construct a 3 by 3 random matrix, I can just use something like this. A is np dot random dot rand 3 comma 3. Okay, so let's just go to this exercise. Uh, which we can probably open. I should have somewhere. Exercise one, two. Maybe I just type it down. So it's just a couple of lines. Just okay. So the first thing which we have to do is the usual thing, and then the second thing is that we want four matrices, right? The problem asking us calculate the trace or product of four random matrices. So four random matrices. Let's just do np.random.rand 3 comma 3, and this I'll just copy this four times. Maybe this is not the most efficient way, but it should work for our purposes here. So now I have four random matrices, and I want to calculate this two ways. So I'll call one of them res1 and one of them result2, and I want to see whether both of them are doing the same thing. So I'll print res1 minus res2. Okay, so what is now res1? I want to compute res1 is nothing but np einsum. I'll explain this notation. So you should not worry. You should just follow the notation and how I am writing, because that will be useful for later exercise and later what we're going to do. So IP. We have four matrices C, and this is going to be D. Okay, so let me just make sure it's all right. And the second way is np dot trace of np dot np dot np dot. Okay, I think there will be some error. We'll fix that later on. Let's just see what it does. Res2 is some problem. Okay, maybe this is so np dot 2 pc. Oh, there are two dots here. Okay, it should be fine. Okay, so we calculated this two ways, and what we see actually is both of them give me the same answer. So this just tells you that einsum is doing what I wanted it to do. And simple example, you can, instead of working with einsum, you can just write down this simple routine uh, of multiplying matrices. So this entire chunk multiplies four matrices A, B, C, D in order, and then takes the trace. This the einsum, what it does is it multiplies A and B initially, right? Two multiplication, and then the product, then the output is multiplied by with C. So I K K J I J, and then the result is multiplied by D, which is I J J P, gives me I P. And once we get that result, we do I, and that means we are just taking the trace. So if I do, for example, if I do np einsum of I of something, it just means that A is a matrix and I'm taking the trace of that matrix. So for example, if I do something like this just means that C is trace A in this notation. Okay. So this is the exercise which tells us that both of these are equivalent ways of doing the same thing. Okay. Does it matter what letters you use? No, it doesn't matter what letters you use. It also will not matter if you remove this part. You don't need to tell it. You don't need to specify it to what it should go. It will be determined by the input. If I write this, it will automatically know that the J index has to be contracted, and it will just give you something which is IP. But I like writing this because now I can do PI. If I don't want IP and I want the transpose of that, so it's better to write like this, because then it is obvious that the index will be changed in the final result. But for our exercise, we could just replace all these like this also, and it should still work and still works. Okay, let's see. You could multiply. Yeah, you need to be very careful about these parentheses, because there, as you can see, it's like uh, uh, yeah, if you are not able to run or you're not getting zero error, you should try to look into these problems, check commas, and I didn't make sure you have only three NP loads and double check. So is like, are most of the people getting it? I assume yeah, so it should work. I'll leave this on the screen for a couple of more seconds, and then you can just see. Okay, good. Both ways should indeed match, because that is what is expected. If we use Einsam, Einsam is a very effective method people use. So we'll also discuss things which are better than Einsam. So for example, Einsam is very slow. There are more faster ways of doing this. And a method which I know, which probably is faster than this, is np tensor dot. So tensor dot is faster than, as you can see, it already gives me the suggestion here: compute tensor product along specified axis. So it does the same thing. It has a different notation and so on, but you can also check this if you are interested. Einsam is not very good when you go to very big matrices or you're contracting big networks. Okay, so this exercise was just an introduction to Einsam, just because you should know about these interesting things which might be useful sometime. So this is the exercise we just finished, and we saw that the result was a result agreed with each other. Okay, so what are the faster alternatives we want to use? The faster alternatives which most of the research groups, and when we write papers, which we use, is we use something called NCON. NCON is a specially written routine for these tensor network contractions. NCON stands for, N is for network, and CON is for contractor. So this is a network contractor. So what is a network? Network is something which I showed you before. So for example, this is a network, right? You want to contract this network. How do you do it? You use NCON. So that is what NCON is going to do. Now, NCON you can download from my GitHub page, or you can download from the Dropbox folder, right? So you should do either of these in the next half minute or so, because we'll need this NCON for all the exercises which we are going to do from now on, right? If you don't have, yeah, you should be able to download ncon.py from either of these methods which I have written down here. Once we have ncon, how do we use it? So let me just try to put ncon on my. So now ncon for we have to okay. So let's just open new notebook. And then you have to click on this folder sign, because ncon is a outside is a routine which we have to upload to Google. If you're doing Google Colab like me, if you're doing Jupyter, there should be some other way of importing that file. If you're doing on your terminal, there should be a way of putting that file in your directory, and so on. So whatever method works for you, you have to do that. But for me, suppose this will work, then I go to file, I have to upload some file from somewhere, and then I go to documents, in which I have this folder, and then I have this ncon. So I just import that ncon uh, to my collab, and it gives me a warning saying that reminder, uploaded files will get deleted when this runtime is recycled. So that's fine, but I'll just upload this. So now I have ncon uh, in my directory here, and when I call it in my code, it'll pick it up, and then we can do whatever we want to do. So now in ncon, if we want to do a contraction like this, say for example, we want to do aijk b pjk. Now you have to notice that j and k are being contracted, and the final result is just a matrix which is cip. The notation which we use in ncon is, we write down the c is equal to ncon, and then we give it two inputs, which is a and b, and then we have this notation -1 2 1 -2 2 1. What does this mean? Whenever there's a negative integer, that negative integer means that index is going to survive till the end. The negative parts here, the negative parts is this and this. So this is telling me that the first index of A and the second index and the first index of B is going to survive the contraction, right? And that is exactly what it should be. CIP, picking up I from here and P from here, right? And this is -1, -2, because that is the order I want. If I want this C to be CPI, then I have to flip this -1 and -2, right? So it goes like in order. The first index in the output is going to be -1, the second index is going to be -2, and so on. Now, all the positive integers will be contracted. So for example, this will be contracted with this, and this will be contracted with this. And that is exactly the pattern which we have here, right? The second is getting contracted with second, and the first is getting contracted with first. So that is the ncon notation which we are going to use. I'm not going to write this on Colab right now, because we'll do some more examples, and then we can follow that. So this next exercise which we have to do: compute the rank 4 tensor, which is given by A R Q B A, which is equal to B I J K L C J I Q R D L K A B using ncon, where all the indices are running from 1 to 3. We also want to draw a tensor diagram of this contraction. So let me just draw the tensor diagram of this contraction first. This is the pattern, and then we just connect the sides together. So you get the idea. So this is like the contraction which we'll have, and then this will give me something which is RQBA. So this will remain, this will remain, this will remain and this will remain. So this is the tensor diagram which you can draw, right? You have to make sure that all the indices, you can organize this and draw it in a neat manner. It's just that I don't want to do it right now. It's just if you understand what I'm doing here, then it serves the purpose. So now, how do we compute this quantity? How do we compute this rank 4 tensor? So let's just we need three matrices, random matrices B, C, and D. So let's do that. But before that, we also have to import the ncon which we used, right? So now, since assuming that you have ncon, we'll import numpy as np, and from ncon we'll import ncon, and then we have a, b, and c. We have, sorry, b, c, and d. But note that they are not rank matrices anymore. They are rank 4 tensors, right? So I need to do this. Now B, C, and D are rank 4 tensors where the indices are running from 1 to 3, right? Because that is what the exercise is asking me to do. It is asking me to compute uh, this rank 4 tensors. So this is B, C, and D rank 4 tensors, all of them random rank 4 tensor. And how do I do ncon now? So I do ncon like this. B, C, comma, D, comma, basis 1, 2, 3, 4, comma, 2, 1, minus 2, minus 1, 4, 3, minus 4, minus 3. And I can also do this einsum way, because now we know how to use einsum. So einsum way is ijkl, comma, jiqr, comma, lkab, going to rqba. So einsum is basically just how you write it. You just, and now what do we want to do? We want to see that both of them give the same answer, and for that we use something called all close. And all close is going to, so maybe I should do this a1, a2. So all close is going to compare a1 and a2, and if they are the same, it will give return a true. Otherwise, it will return false. So let's just run this. So this is true, right? So this just tells me that both of these are doing the same thing. Einsum ijkl, jiqr, lkab, rqba. Now let's again look at this ncon convention. There are 4 indices which will survive contraction. So rqba, and those are located -1, -2, -3, and -4. This is the exercise which contracts this. Okay, so let's just take the questions now. Okay. Okay, so okay. Yeah, the advantage of using ncon over the previous methods is that ncon is much faster. It can uh, is just first of all, it doesn't use einsum is slow, so it doesn't use einsum. It uses efficient matrix multiplication routines of numpy, and also tensor dot. So it is a, and the good thing about ncon is that you can just throw it any rank tensor versus any rank tensor, it will give you an output. So you don't have to worry doing a tensor dot, because tensor dot just takes two arguments. uh, INSUM can take multiple arguments, multiple input tensors, but it is slow. So ncon is like, you can do for any number of input tensors and it will do it quickly. So it's just a routine. If we go and look into the ncon routine, we'll just see that it just uses some matrix multiplications and other things. The reference for, so ncon was first given in this paper, which look at this from archive 14020939, and this was what everyone uses. And it's like, once you have convinced yourself that this is giving the same answer as you expect from INSUM and tensor dot, it's just faster. There are other faster ways, but like this is reasonably faster than any other available routine. Okay, so what is okay? Does all close avoid the problem with rounding error being used in equalities? Yes, it does. It does. I think it rounds off. The all close also has other arguments. So, for example, you can already see here. If I click here, you can see that there's R tall, there's and there's 8 tolerance and so on. So, assuming these things take care of what you are asking basically. all, all close is very indeed it's very useful because it's very easy way to compare two matrices. Now, because the problem is, if I just, now I can also do this print a1 minus a2, right? If it throws me 0, I know that both of them are doing the same thing. But you will see the problem with this. The problem is this: it's 0, but it's 0 in a weird way with minus 50 machine precision minus 15. So if it is a rank, this is a rank 4 tensor. Now if I'm multiplying a rank 20 tensor or rank 10 tensor, then if I want to see whether they are giving the same, it's absolutely crazy to do it that way. So we don't do this, we just use all close. Okay, fine. So this exercise is was in to show you how N1 works. Let's just carry on. Okay, so now we come to the idea of, I have 15 minutes left, so maybe I'll finish in time, at least where I intended to finish today. So this, we come to this idea of fundamental tensor. The idea of fundamental tensor is that in D dimensions, in classical D dimensions, we are on a Euclidean lattice in D dimensions. The fundamental tensor has a total of 2D legs. It's just because left, right, up, down, or top, bottom. So if you're in 3 dimension, there are 6 legs. So it's like 2D. So for example, let's take a 2-dimensional fundamental tensor. It will have 4 legs. Okay, so this is left, this is right, this is up, and this is down. The location of 4 tensors, right? Now, in 3 dimension, it will become L, R, U, D, forward and back. So 6 legs of a fundamental tensor. The way we don't denote this tensor, rank 4 tensor, is by writing LRUD. So left, right, up, down. Or we can also use the clockwise notation, which starting from say 9 o'clock, and this will give you LURD, right? And similarly for this, LRUDBF, or whatever way you want to orient that. You can fix the convention at the starting of the any numerical work you want to do, and then you can stick to that and then contract the tensors based on that. So depending on what the situation is, we'll follow some pattern of indices. So this is the fundamental tensor. What is the fundamental tensor useful for? That is something which is important to mention. The fundamental tensor is useful because once you write down the fundamental tensor for, say, for you, suppose you want to uh, study the thermodynamic properties of 2D classical Ising model, you have to first write down a fundamental tensor, and then you have to take that fundamental tensor and multiply many of those tensors together to go to the thermodynamic limit. So we'll show later on how that works. So for example, this is how it works. You take one tensor So suppose in this exercise, T1 is equal to T2 is equal to T3 is equal to T4 is equal to the fundamental tensor. Now, if four of the tensors are the same, I started with one tensor, but now I have four, right? So when I go from this to this, I'm actually going from one lattice side to four lattice sides, right? So this one step is also known in the literature as one step of coarse graining, right? So we are doing one step of coarse graining. We start with some tensor, and then we take four of those tensors together like this and contract it and come up with some tensor. So for example, the resulting tensor still has four legs: -1, -2, -3, -4, right? So you again get rank 4 tensor. And if you do this coarse grading process a large number of times, you get to the thermodynamic limit, starting with this fundamental tensor, which is given by T. Note that when we want to use this notion of fundamental tensor, there are certain things which should be true. First of the things is that you should have the proper translational symmetry of the lattice. So for example, if you have a square lattice and there are some defects lying on somewhere inside the lattice, then you cannot use this process, right? Because then you have to take into account that there's no translational symmetry, and then you have to do more complicated stuff, which we will not talk about in these lectures. For in these lectures, we always assume that there's translational symmetry, and there's one tensor T, which we start with, can get us to the thermodynamic limit, and we'll see how that works. Okay, now we do this very important exercise, which will be very useful for the next things which we do. We want to contract this network using ncon. So this is something I won't do it myself. I'll just open the Colab page. I strongly encourage you to do this yourself because this is very important, and now we already know the basics, right? So first thing is that you should set a notation here. Set a notation. For example, you can say that I'll choose this notation: I J K L P Q R S, right? So for example, let me just write down. If I take this T1, I J K L, and then I have T3. Note that the J of Ti is going to be the second index of T3. So placeholder, 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 placeholder. But this is J. This can be something. The third index of both of them are the same. Fourth can be something else. So this is how I write Ti ijkl T3 pjkq, right? Do the okay, let's see. Do the dotted lines in that diagram mean anything, or are they same connections as the solid lines? So solid lines is the legs of the tensor. The dotted line is the contracted indices. So whenever you see a dotted line, that means the contraction is happening over that. So I'm representing the contractions with lines or dotted lines. And if a solid line does not contribute to any dotted line, then it is the index which is going to remain after the contraction. And there are only four such uh, legs like that. Right? Okay, so let's see what is the ncon equivalent of this diagram. So you can execute this using a single line command. You can take rank 4 random tensors, and then we can uh, contract this. So I'll as an exercise, because this is everyone should be clear on how to do this at the moment. If you're not clear, it will anyways pop up in the algorithm of 2D classical Ising model, so we can look at it more closely at that time. Okay, so let me just move ahead. Okay, so tensor networks coarse graining algorithm, as I already told you, we start with some fundamental tensor and then you coarse grain and you get to the thermodynamic limit. And this was initially following the work of Wilson on RG and then density matrix renormalization group by Stephen White in 92. There was a surge in using tensor networks as these coarse graining algorithms. And that was done in this work by Levin and Nave. And after that, it was extended along various directions. The algorithm which we are going to use for our purposes is known as higher order TRG or HOTRG. Higher order TRG means that it's just a fancy linear algebra word in the sense that you're taking going to when we are going to do the coarse screening, we'll take something which is higher order decomposition, not the first order decomposition, right? As usually done. It increases the efficiency and improves on the error of the coarse screening. And the algorithm is based on this paper in 2012. There are many other tensor networks method known as MPS, PEPS, TNR, TEFR, GILT TNR, and many others. The basic idea is why are there so many different methods of doing the same thing? It's because different contractions and how you understand the physics in the thermodynamic limit depends on what kind of system you are looking at and and the accuracy you want. So, for example, if I want to look at some system which is close to the second order critical point where the correlation lengths are going becoming large and very large and tending to infinity, then probably this method will not suffice. So we cannot use this method if we are sitting at the critical point and want to even understand some spin model system. And that is because it is going from a gapped system to a gapless system, right? The gapless system has infinite critical correlation length. Uh, mm, and then if you have infinite correlation length, then the coarse graining becomes very tricky. And for that, methods like TNR was devised. So TNR is something which works very well, even very near to the critical point. Whereas this method by Levin and Nave, and to some extent this method by which is called HOTG, only works for gapped systems, right? Okay, so now okay, got it back. So now let's look at this. So I have about 5 minutes in which I can discuss this basic structure, and then we'll go back to the course training coding later on, maybe starting tomorrow. So now what we want to look at is consider T1 equal to T2 equals to T3 equal to T4 is fundamental tensor, right? So this is, for example, T1, T2, T3, and T4. But all of them are the same tensor, right? So their legs and everything else is the same. Now, what constitutes one step of coarse screening? I told you that one step of coarse screening means we take four of these tensors and make it one tensor, and then take that tensor, make it four copies, and make one tensor. So these are one step of coarse graining which is happening. Okay. So now, if we are on a two-dimensional lattice, we have to do coarse graining along x direction and y direction, right? So that is why you see two lines here. The first is, let's see, four tensors. We take like this. The dotted lines are representing the contraction. So we get a rank 4 tensor again, where this is the same as this. So -1, -2, -3, -4. So this is -1, -2, -3, and -4, right? But now the problem is when we -1, -2, -3, -4, we want to do a SVD of that. SVD is a method of reducing a higher rank object to a lower rank object. And SVD is an integral process part of this tensor network algorithms, right? Because if you don't do SVD and you keep on coarse graining, your tensor will grow in size such that after some steps of coarse graining, you'll run out of memory. So as you do the coarse graining, you also have to truncate, right? And you have to truncate based on singular value decomposition, SVD. So how do we do that? We have four legs remaining, right? So left, right, up, left. So one, two, three, four. Once we have that four legs remaining, we take two tensors, two fundamental tensors like this and this, and then we do SVD. So SVD is a method in which, so we'll discuss SVD in more detail tomorrow. So SVD will give you something like a rank 3 object, which is like this. So this is coming from SVD, and this is coming from SVD. And once we have these things from SVD, we'll stick it with these legs such that we eventually get rank 4 tensor again. But the difference is that these are of lower rank. D prime is of lower rank. D is the original size, and D prime is the lower rank. So we are applying SVD along this direction. So it is reducing the dimensionality of that leg along that direction. And then we do it along this direction. And that's why you see triangle like this. So we'll come back to this tomorrow in more detail. And tomorrow we'll start from this exercise, uh, uh, this notion that when all the tensors are the same and they're equal to the fundamental tensor, how do we do the contraction? Once we have this, then we can go and try to do our two-dimensional classical easing model, right? So if you want to check, you can check what SVD actually is and how we are going to do it. But this is what we are going to do tomorrow. We'll do SVD and then we'll solve a 2D classical easing model. So I think I should stop here.
All right, great. Thank you for the awesome talk. And yeah, hope you have a good day.
Are there questions? Oh, okay. So yeah, so today this is lecture 2 of this tensor networks algorithms and applications lectures. Uh, I'll just start from where we left yesterday. Okay, so so this was the page on which we finished yesterday, and this is where I'll start. So let me just start by saying that yesterday I mentioned that when you have this initial tensor, which we have already set up, so something like this, which has four in 2 dimensions, then what we do is we take four of them together, right, and action pattern. So all the dotted lines are the indices which are going to be contracted. Once we do that, we have four remaining indices, right? 1, 2, 3, and 4. Then what do we do after that is that we combine the first two indices into one index and the third and the fourth into the single index. So what we do is we make a matrix out of four indices. So we'll see how this works more closely. Okay, so what constitutes one step of coarse graining? So the steps are outlined in this slide. So take initial tensor, which is some Tn. Let's call it as Tn. We'll understand why I call this Tn later on. Now combine four of them like I just mentioned before. So I take four of them. Now this D refers to the extent of the indices. So the indices will run from 1 to D. So this is 4 index object. So the total number of elements will be D to the 4 for this one, D to the 4 for this one, and so on. For all of them, there will be d to the 4 elements because every index is running from 1 to d. So I take 4 of these tensors and do this contraction to get resulting tensor, which I label as -1, -2, -3, and -4. Right? If I do this, I'm doing a coarse graining along x direction. If I rotate this setup by 90 degrees, then I'm doing a coarse graining along y direction. Right? Now, as I mentioned, this is -1, -2, -3, -4. I'll take both of them together, and I'll get a matrix. So step 3 is combine -1 and -2. We remember from yesterday the notation which ncon uses. -1 and -2 are the first two indices of the output tensor. -3, -4 are the third and the fourth indices of the output tensor. And we construct a matrix out of that. Then what do? We do a singular value decomposition of this matrix. So singular value decomposition is a specific form of a decomposition which you can read about online. It just takes some it just takes a matrix and then breaks it into three components. Uh, so any matrix can be represented like this. So let's see. So these are U, S, and V are matrices, and S is the singular values. So what do? Then once we have this SVD, so SVD of that matrix, and the SVD will have three indices. These are the three indices of the SVD tensor, and then three indices of this of the same SVD product. And then we take two of the tensors, this one and this one, and construct a rank 4 object again. So this is one free leg, one free leg, one free leg, and one free leg. And that will give us Tn plus 1, right? And this is one step of coarse graining. So we are going from n to n plus 1, and that is why we say that this is one step of coarse graining along x direction. We have to do a similar type of coarse graining along y direction also, right? And that is done like this. So for example, this tensor, which is marked in this asterisk here, is something like this. When you do a pi by 2 rotation of that, you get a setup like this. So -1, -2 was, so this was -1 and -2 here. Now you have -1 and -2 on the top, right? So this is pi by 2. So this is along direction. And this was along x direction, right? So these are two steps of coarse graining which we do. Let me make few comments and then we'll go to the coding part where you'll explicitly see how I'm going to code this up and this part as well. So let me make few comments. So singular value decomposition is the most expensive part of this computation we are going to do. So of any tensor network calculation, SVD is the most expensive part. SVD is tricky because SVD takes the maximum amount of time of a calculation, and it is not very easy to parallelize or make SVD more efficient, at least as far as I know. There are some different methods which can speed up a little, but still that is the bulk of the calculation. So at every coarse graining step, we normalize the tensor. So what does that mean? That means if I start from a tensor, say Tn, and I get to a tensor Tn plus 1, and I don't normalize, then eventually after few steps of coarse graining, it is going to blow up. So what I do at every step is that I take the tensor and divide it by some normalization factor. Now, normalization factor can be anything from greatest element of that uh, tensor or the norm of that tensor. So we'll see that in the code explicitly when we get to code. So what was SVD? SVD was matrix. So M is a matrix which has two legs, say D square, D square. And then you do SVD, you get decomposition like this. U, lambda, V. Lambda contains all the singular values. Now D, this leg has dimension D, this leg has dimension D. So you see that this piece has d to the 4 elements, but the output only has d square, right? So we are reducing the rank of the overall tensor. So that means we are doing some sort of a truncation. So this is the step of the truncation. SVD is where in tensor networks we do the truncation. It is important, it is necessary because we cannot store the entire tensor in its full form because of the reasons we discussed yesterday, that the Hilbert space is very big. So we need to contract or reduce the space efficiently so that we still have the physics, but we don't have to deal with storing infinite, like exponentially big indices. So this is the step of SVD. So now what we are going to do is we are first going to look at this two-dimensional classical easing. Two-dimensional classical easing model is a simple spin model where you have x and y direction, and there's a next to neighbor interaction. So it just has a simple term like there are spins at two sides and they talk to each other with some exchange energy and so on. And it is at some temperature, which is, for example, inverse temperature is beta, right? And that beta is entering into this. So for example, there's a matrix, there's a 2 by 2 matrix which we'll consider, which is given by this object cosh beta sinh beta square root, and the same terms with opposite signs in the lower row. And then what do? We take this 2 by 2 matrix and we construct this object. I cannot go into the proof of this. For now, you have to believe me that this is true. I'll show you that this is indeed true by showing you that it reproduces the exact result. So Tijkl, which is the fundamental tensor for the easing model, two-dimensional easing model, is constructed like this. WPI, WPJ, there's a typo here. This should be K. Okay. So P, 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 P contracted. I will come from here, J from here, from here, and I get a rank 4 tensor, right? Now note that the most important object which we look at in any tensor network is the partition function. So how is the partition function going to come up? Partition function, which is denoted by this Z, will be a tensor trace. So this TR is known as tensor trace. So this is for tensor. This is the usual trace. So tensor trace of Tijkl at each lattice site multiplied. So we'll do the coarse graining and multiply a large number of lattice site at each coarse graining step. And then eventually we'll take the tensor trace of that object, and that will give us the partition function. There is also an interpretation of the partition function in terms of transfer matrix, which we know, which is given by this expression. Z is equal to the trace of transfer matrix raised to the number of time slices, or number of, which is NT, so number of sites along the temporal direction. So this is the identical. So this Z should be the same Z as this one in the thermodynamic limit, right? So this is the Z which we'll consider. Now it is important to mention here that when we do Monte Carlo simulations of gauge theory or spin models, Z is not accessible. We don't look at Z. We cannot find out what Z is. We always look at some expectation values when we do Monte Carlo simulation. Maybe it's magnetization, maybe it's something else, magnetization square or something like that. But if I tell you find Z in a Monte Carlo, it's not possible. But for tensor networks, Z is probably the most natural quantity. It's the quantity which you get once you coarse grain and go to the thermodynamic limit. So as you can already see, once we have Z, calculating the free energy is trivial because F is just going to be T log of Z, right? So calculating free energy is very straightforward in this tensor networks, and we'll try to calculate that now. Okay, so for that, now I should mention that for this two-dimensional classical easing model, there is an exact solution, very famous exact solution due to Onsager. and it's 1944 paper, uh, on a square lattice when there is no magnetic field. So this is in all in H equal to 0. And we'll set the Boltzmann constant Kb and the exchange coupling J equal to 1. And in that case, the critical temperature of two-dimensional Ising model is given by this value of beta. So this value of beta should be what we should be able to see in tensor networks as well, right? Exact free energy is known. So when we compute the free energy using the tensor networks, we can check that we are doing it correctly. So we'll compute F, and then we'll reproduce C at the critical inverse temperature using tensor networks. So that is our goal for the moment. Okay, so now to do this, we have to write a function to do one step of coarse graining. So what it will do is it will take some input tensor and it will give me an output tensor and also the norm, because I told you that at every step we have to divide by the norm and we have to store the norm at each coarse graining step because that is important to calculate the free energy. So we write a function which is something like this, and we have to write another function for calculating or constructing the input tensor, which will take beta as input, right? Because as we saw here, the input tensor is just going to depend on beta. It's just a function of beta. It's just a function of beta eventually. So we'll write a function in Python which will take beta as input and give me t initial for this two-dimensional classical easing model, right? Okay. So I think we should now go and so there you should load the ncon as we did yesterday, and then yeah, yeah, I think that should be fine. There should be another file in the Dropbox folder which is called svd. You can download that. uh, I'll that I'll on my screen, so you can just follow it on my screen if you don't have svd. So let's just start that and see what we get. Okay, so let me first load uh, ncon. Are there any questions to know? Okay, so going. So I've already loaded ncon, and then I will get just a second. Okay, it should be here. Okay. Okay, so I need something for the instructions, which I'll just copy from here. So I don't want to. You can see on my screen what it does. So I'll write some text here. Hopefully this should work. Okay, it works. So now let's see. We can go back to code. Okay, so this is what I wanted to write. Just initially, I'm just writing what I explained. WIA is given by cosh beta sinh like this. Then we have TABCD, which is like this. Now the exact solution, there are different expressions for exact solution, which is available in the literature, starting from Onsager's work. But one of the expression which is compact is given by this. So the free energy density for two-dimensional classical Ising model is given by -1 by beta log of 2 cosh 2 beta minus kappa square. Kappa is given by this function, sinh 2 beta by 2 cos square 2 beta. And this is some hypergeometric function of kind 4-3. This is generalized hypergeometric function. You don't need to worry about these things. I'll just show you that we reproduce the correct answer. That is what we are interested in. The critical temperature is given by this expression, Tc 0.2691. This is all for square lattice, and that gives us beta C is equal to 0.44069. This can also be obtained by solving sinh 2 beta c equal to 1. So if you put the beta c value on this, you'll just get sinh of 2 times 0.44 will give you 1, right? So these are the exact results which we know. Now, for our purposes, it's important that we just check for one of the temperatures that tensor network is reproducing the right result. So for that, I have to open this Mathematica file. You don't need to do this. I have already coded this up. It's just for demonstration in the sense that we want to know what is the value, say at 0.5. So these are 4 different expressions available in the literature for the free energy density in the thermodynamic limit at temperature B. I don't write beta here, I just write small b. So if I execute this, I get some answers here, which is like this. So the exact, I don't know why this is giving 0. Maybe there's some protect, I will check. Some commands are protected. Okay, whatever, it's not important. The thing is that all these expressions give me the same answer, which is this, right? So I'll just copy this answer and paste into my code just so that I know exact result at beta 0.5 is this. So this is just that I want to check later on, and then we don't need to worry about Mathematica anymore. So let's start to write the tensor network formulation for two-dimensional classical easing model. This will take some time. So just I'll just copy the initial part, which is just standard. I'll make this notebook available later on so we can just all see. You can also type this. So I'll explain as we go along. So we import bunch of things. For t equal to 2, the free energy for 2D easing is this number, 0.05159 or 58, whatever. We have checked that this is the result using exact expression. Now, what do we do here is now we have to define something called number of iterations. So number of iterations is 12. The magnetic field is 0 at the moment. We don't do it in the magnetic field because the exact result is for 0 magnetic field. D is equal to 8 is right now the size of each of the leg, right? As I mentioned, when we do truncation, we reduce the size of the leg. So we'll reduce the eventual size to 8, right? Because we start with, as you already saw, this is a 2 by 2 matrix, right? So A, B, C, and D are running from 1 to 2. It's just a 2 to the 4 tensor right now. But it will become 4 to the 4, then it will become 16 to the 4. And once it crosses, we'll truncate it back to 8, right? So at any given step of course, 8 to the 4 will be the maximum number of elements in that tensor. So that is what this D stands for. So these are the preliminary things. I just to note the time it takes, I just write this command, which will print the time, start time and end time. So now I can go and copy the the thing which you have in the Dropbox folder, which is the SVD. So I'll go to the Dropbox folder. I'll just go to this folder. I'll just copy this. So I get this function here. Now this function tensor SVD is, as I told you, is going to reduce the rank of the tensor. So it will take some input, then it will take some make a left index and a right index. We need 2 indices because this is a matrix. And then this D is what I just explained, this D. So it's going to truncate it to this value, right? And it will give me the 3 elements of the output of SVD. So whenever we do SVD, you get 3 output, U, S, and V, as I already mentioned in the note. So this is the SVD routine, which we want to use for our purposes. Now, there are 2 routines which we have to write. So first of them, one of them is this 2D easing model. So let's just write capital. and then it takes as input beta, as I already mentioned, right? So what is this going to do? This is going to, let's say we construct this something called A, which is NP square root of NP cosh beta. And then we construct something called B is equal to sinh beta. And then what do? We want to calculate, construct this W. And how do we do that? We just do it like this: A comma B, B comma, right? That is what we do here. So let's see. So this is A, B, A minus B. Okay, so A, B, A minus B. So this is what we get. And then what do we do? Then we have to do some out tensor, which is just NP einsum. We'll use einsum here for this function because it's just a small size. It has 2 to the 4 elements. So we can use einsum easily, no problems. So this is IA, comma, IB, comma, IC, comma, ID. And this will give me A, B, C, D. There should not be this thing here. Okay. A, B, C, D, right? And then what do we do here? We just write 4 times W, right? Okay, so this is the out tensor, and this function will return out, right? So this out is nothing but our Tijkl, the initial tensor. This is one routine which we had to write. Now we come to the second important routine, which is one step of coarse graining. So let's call it as coarse graining step. It will take a matrix as input, or it will also take a second input depending on. So for the moment, it can just take one input. And what is that going to be? It's going to be, so let's say T is going to be that matrix, and then I construct AA DAG, which is going to be the network contractor of 4 of the T's, as I mentioned, right? So this is coarse graining along X happening right now. Okay, so this is comma, and the net pattern of contraction is something like this: -2, 1. I'll just show how I'm writing this in a moment. Just let me write down, and then 1, 5, 3, 4, -4, 1, 2, 6, and the last answer is -3. You can already see that there are 4 negative integers. That's because the output tensor is going to have rank 4. And this is, so now let's just go back and show you why I'm writing something like this. For example, I can go to this. Hopefully this will work, right? So this is exactly what I have. So let's see. So I start with this tensor, and the order I follow is clockwise, starting from 9 o'clock. So this is -2, 1, 2, 5. -2, 1, 2, 5. Then I go to this one, which is -1, 5, 3, 4. -1, 5, 3, 4. Then I go to this one, the third tensor, -4, 1, 2, 6. -4, 1, 2, 6. And then I go to the fourth one, which is -3, 6, 3, 4. -3, 6, 3, 4. Right? So this will give me a 4 index object from this, and this is what I called AA DAG, right? Okay, so that is good. We have done that, but that is not all, because now, as I mentioned in my notes, I have to do a SVD of this. So I do a SVD. Let's see, there's some discussion happening here. Let me just go back to the chat and see what is the issue here. Okay. Yeah, the S. Yeah, yeah. It should be there. I can also maybe I'll just try to also copy it in the chat box for people if you don't have access to the thing. Let's probably not the most efficient way, but it's okay. Okay, so let's go back to what we were doing here. Then we do a SVD, as I mentioned to you. USV will be the output of the SVD, and then we use our routine, which we just already mentioned. So we do a SVD of AA DAG, and I told you that out of this rank 4 object, we are going to construct a matrix, right? So we'll take 0 and 1 index together and fuse them into one, and then we'll be using for the second and the third, and we'll use D because we want to cut it to D, right? Tensor SVD takes 3 arguments, as you can see here. Input tensor, left and right, what do we want to make of left and right, and then D, right? So we give it a rank 4 tensor, but we tell this routine that you have to take 0 and 1 combine and 2 and 3 combine, so it becomes a matrix, and then truncate it to D, right? Now this is an interesting step where we construct this piece. So let's just go back to the notes. Okay, so now after SVD we have USB. So this is U, this is U, this is T, and this is T, right? So now I have to take this U which is coming from SVD, this U which is coming from SVD, and fuse it with 2 fundamental tensors to complete one step of coarse graining along the X direction, right? So let's do that. So now A will be my ncon of U, comma T, comma T, comma U. Now I need to mention the indices here. So let's do that. 1, 2, minus 1, comma 2, minus 2, 4, and 3. And then I have to write down another T tensor, 1, 3, 5, minus 4, and then another U tensor, 5, 4, minus 3. Okay. So as you can see, U is a rank 3 tensor. So it has 3 numbers. And as you can see, there's just one negative because it will only have one which survives, and that is minus 1. And this is minus 2, minus 3, and minus 4. Right? Okay, so this is one step of coarse graining along the X direction. Let me just make sure that everything is correct. Minus 2, 4, 3, 1, 3, 5, minus 4, 5, 4, 3. Yes. So this is along X. Now we do something along Y, but I won't write down entirely. It's not the same, but I'll copy this. And now I'll write it down along Y direction. So these ordering will change. This is left as an exercise for you to convince yourself that this is indeed true. I do it on at the moment because you will have the notes. I'll put the lecture notes also in the Dropbox folder. So you'll have the notes. Basically, what I'm doing right now is I did this, and now I am doing this. This is along Y direction, right? So this is what I'm doing in this part of the along Y direction. So just copying it from my notes. 1, minus 1, 2, 3, 2, minus 2, 4, 5, 1 minus 3, 6, 3, 6 minus 4. We should not repeat any negative integers, and we should always repeat a positive integer because that will be contracted over, right? So that is correct. And then we take this line doesn't change, it stays the same. This will be 1 2 minus 2 minus 1 1 3 and 4 3 2 minus 3 5, and this will be 4 5 minus 4. So this is along y. So now we are done, and as I promised you, we have to divide this by the norm. So how do we divide it by the norm? Let's take the maximum of, so let's call this AA. So A is after coarse graining along X, AA is after coarse graining along Y. So we take the maximum of AA, and what do? We divide it by max of AA. This is the normalization step. And then we return two objects, AA and max AA. Right. This is one step of coarse graining. Now we have all the function which we need now to proceed. I just have to use the main routine for this code, which I have printed out, copied here. So I just, the main routine is a little complicated because it is also going to plot different things, which we'll see. This is the main routine here. It's here on line 83, as you can see in my notes. So we'll generate different beta, and then we will use some n steps. We'll write, generate a list which is f, which is going to compute the free energy for different beta, and then we are going to have a loop for p in range 0 to n steps. What is it going to do? It is going to, let's just print beta for the moment. We'll check if it is okay or not. Okay, before that, I should just show you that we reproduce the result which we promised that we will reproduce for 0.50. So that will take care of that. And then we have, what do? We construct the initial tensor, which is just the function which we wrote, z2d easing. We normalize that tensor. We divide by the normalization. This is something which we don't need right now, so we can just delete that. And then we compute z. Now z is a number. Z is a partition function, it's a number. So if it is a number, you see that there is no negative sign here. All the indices are contracted. And how do we construct z? We construct z like this. Couple of steps ahead. Yep. So you construct z like this. You see this part here. Don't look at this part. Don't look at this part. This is for some other model, but the contraction pattern is just like this. So this, we have 4 tensors, and this is how we contract them. All the dashed lines are the contraction. Now this gives me a number, right? And that is what z is. Okay, so we'll come to that later on actually. Okay, so we are sort of here, right? Okay, so let's do that, and now we should be run this and see what it does. Let's just try to run this if there are any errors. Okay, unintent doesn't match on line 55. Okay, I see why. it should match now. Beta p. Interesting. So C2D easing beta p. What's the problem? 9315. Let's just compute it for say. Okay, so 59. Okay, I think the problem is beta p. Z2D easing is oh, maybe the problem is here. No, Z2D, what am I giving it to? Oh, it should be fine. You need an extra set of brackets on line 59. Yeah, I think you're right. Yeah, absolutely, you're right. Thank you so much. You're absolutely right. It still gives an error. Come on. Oh, Tim is not defined. Okay. So that is why. Let's see. I'll just define TIM randomly. We don't need to worry about what TIM is. I'll just define. So TIM will come to this later on. We won't have probably time for this, but TIM is impure tensor. So when we want to compute, say, for example, partition function, we don't need any impure tensor. But if I want to say calculate magnetization, I need to also coarse-grain the magnetization tensor, and that is what this impure is. We don't need to worry about that. I'll just see that this CG step takes 1. Okay, so I should go back and yeah, that's why I should not have modified. CG step is taking 2. So I just something like in 2, and then I do something like TI, just randomly adding. So that okay? So what is the problem now? Do check indices. Okay, so I think instead of like let me spend a minute on this. Okay, so let's just go back to the thing which I already had working. And since we know, let's just see. Okay, so I'll just try to run this. All the ingredients which we know already there. So let's just try to run this for 50 to 52 to check that we are doing correctly. Hope this runs. Okay, this runs. Okay. Okay, so let's see. There's an error here which I already see here. So the initial tensor, this is yeah, you don't need to see check this. This is for some magnetic field we're not worrying about right now. So the tensor for this case was just A, B, A minus B. So this is A, B, A minus B. Okay, so for 0.5, what do I get for free energy? I get 2 minus 2.05158. What was the exact value? Exact value was minus 2.05158, right? So we have reproduced Onsager's result for this t equal to 2 using tensor networks, as you can clearly see, right? This has all the steps which we talked about. So for example, let me just go back to this main routine again. So we generate beta, and then we are computing this initial tensor, and we're dividing by the norm, and we are computing this partition function, which is just a number. And then we have a C, which is the log of the normalization. And this is the formula which you can just take me for my word right now, is how you compute the free energy using the normalization constants and the partition function z. uh, and then you do this coarse graining number of iterations time. So for example, if I do this, let's see, if if iteration is 10, then eventually we have 2 to the 10 times 2 to the 10 lattice. Right? If you do this 20, you have 2 to the 20. So if you take this to be 30, it's very easily the thermodynamic limit. Right? So people also do it and 2 to the 50. So you will see a lot of tensor network calculation being done on a 2 to the 50 lattice by 2 to the 50 lattice. So it's not very ridiculous. At least in 2 dimensions, you can do that. So this is what we get. So once we have convinced that we the exact result, now we want to look at how we can compute the critical temperature. So for computing the critical temperature, I have to run this code for some range of beta. Let's just run it for 0.38 to 0.48 with 0.0005 increment. I just want to mention here that d is equal to 8. Is there a way to automate, let's see, is there a way to automate the indices that go into ncon, or do you hand draw transaction and then so there is a way, there's a website which I don't remember right now, but there's a website which has nice contraction patterns, and you can just feed it a diagram and it will throw you the ncon pattern. So that is the only way. So you give it a diagram and it will give you the ncon code which you need for that. So that is what I know. I'll send you the link later on, once we finish this lecture. Okay, so let's and then uh, yeah. So d is equal to 8. Iterations is 12. So for example, we are doing classical Ising model on 2 to the 12 by 2 to the 12 square lattice right now in with zero magnetic field because H is equal to 0. Okay, so now I'll run this and we'll see what it does. So it is computing free energies for different value of beta 0.38, 0.3805. You can see this is going really fast and on going to 0.48. And then what it will do is it will compute the free energy, compute the first derivative of the free energy. So this is the free energy, right? Versus inverse temperature. Now, in the code, once we have the free energy, I'm also calculating the internal energy. So internal energy is basically, how do we define this? So we are now at this point. So once we have Z, we can compute ln Z. And if we take the derivative of ln Z with respect to beta, we get energy. And then you can also take the second derivative of that. So this is done by a numpy gradient function in the code. So you do np gradient of Z as step size in beta, you get this. And then you do the gradient function on E to get specific heat. So this is what it is doing. So this is numpy's gradient function, and you do it like this. So in the code, we are doing this step. So this is df by dx. We are assuming equal spacing of beta, right? Which is 0.0005 in this case. So we do np gradient f comma dx. Dx is d, which is 0.0005, as you can see. And then you do the same thing for internal energy, df by dx. And then you do it for uh, specific heat, which is d2f by dx square, right? And let's look at the results. So this is the free energy, this is the internal energy, and now we have the specific heat. And just look at the value where the specific heat is peaking. So this, I'm also printing this out. The specific heat peaks at 0.04405, right? The exact result, as I told you, was 0.04407. So you can already see seconds, I'm able to reproduce the exact result. To be more precise, I just need to increase this number slightly, and then we do the same thing. And so this is basically, we have solved the 2D easing model in like under a minute. Now, if you start doing this on a Monte Carlo, take a it will take a lot of time. You need parallel computers. So this is where the tensor network is really effective. If you can identify the right fundamental initial tensor and then you can coarse grain it, it just does magic. You can just do things very quickly. Another advantage of using tensor networks is that Monte Carlo is a sampling method. So you have problems due to sign. There's a sign problem when the action becomes imaginary and so on. This method is exact. Whatever error is in the computation of free energy here, the truncation, right? And even that error is very small. So there's no error bar, technically speaking, on these free energies. So this value is very close to the exact value which we know from Ansager's work, right? So this is the tensor network calculation for 2D easing model. I'll put this on the Dropbox folder so you can play around with it. You can also do this in presence of magnetic field. I'm not going to discuss that because that is slightly tricky. But as you can guess already, you just need to modify the input tensor and then try to do the same step of coarse grain, right? Okay, what we wanted to do. So we have computed all these things and we have checked that we reproduce the exact result. So you can refer to this paper on arXiv and you will see that it reproduces the same plots as we just made. So you refer to this arXiv and see figure 3 if you're interested. Uh, okay, so another model which I want to talk about, which probably we won't be able to finish, but which is interesting, is 2D classical XY model. So right now we were looking at easing model. Easing model, at each lattice site, the spin can take values +1 or -1, right? When we go to 2D classical XY model, the classical XY model is something like this, which you see here. So you have a square lattice, just like the pages of these notebooks. And at every lattice site, so these are lattice sites here, for example, you have a spin which is oriented along some direction, which can go from 0 to 2 pi. Right? So this is along some direct angle, this is at some angle, and so on. And there are spins at each lattice site. For example, the Hamiltonian for this XY model is given by this expression here, which is H is equal to -j cos theta I minus theta j. And this model has O2 symmetry in the sense that if you take this two-dimensional square lattice and rotate all the spins by same amount, the Hamiltonian doesn't change, right? Because it depends on the difference of these two angles. So this has O2 symmetry. But you can also add a magnetic field to this X5 model, and that breaks the O2 symmetry, right? Because there is now a preferred direction because I'm adding a term which is H cos theta I. So this classical XY model, I recently studied this in this arXiv paper a couple of months ago. And you can read this paper if you want to know more about this model. So I'll just talk about, the basic idea is the same. We want to do a tensor network study of this. And this model also has a phase transition. In fact, a very famous phase transition, which is known as BKT phase transition, which was also the topic of the 2016 Nobel Prize. And it's a very famous transition in condensed matter physics, statistical physics. So why do we want to study this using tensor networks or any model using tensor networks? Because using effective coarse graining algorithms, we can do physics directly in the thermodynamic limit. For example, in the previous paper, I studied this model on a 2 to the 50 times 2 to the 50 lattice, right? And we can reproduce results which are like which are in the same ballpark as Monte Carlo methods within a matter of hours, right? So it's more efficient. how are we going to construct the fundamental tensor for this case? Now, the fundamental tensor for XY model is little more complicated. It's complicated because you have now the special function which forms the initial tensor. So since we are already again in two dimensions, there are four legs of this tensor IJKL, and it again depends on like the Ising model. But now what you have is you have Bessel function, Bessel function I, and you and then you have another form which is depending on which depends on the magnetic field and temperature, which is beta h, and it depends on this indices. Now, if h is equal to 0, I Bessel function I plus k minus j minus L 0 is only non-zero when I plus k is equal to j plus L, right? So that means when these two indices are the same as these two indices. What do I mean by same? I mean by same as in these indices are running from 1 to t, right? When the index numbering of this plus this is plus this, it will contribute 1, otherwise it will be 0. So I'll show you in the code how that works. If it is 0, it's just a delta function as written here. So it's delta I plus k, j plus L, and this is h equal to 0 limit. Now, ideally, when we write down the fundamental tensor for this 2D XY model, I, j, k, L are running from minus infinity to infinity, right? But that is not possible. We truncate it from minus n to n, and then we note do the calculations for different values of n and see how the error changes. For example, we try for n equal to 15, n equal to 20. So in the paper, we did this for n equal to 53, n equal to 26. So we go from minus 26 in steps of 1, crossing 0 to plus 26. So there are a total of 53 indices in this T tensor. And so therefore the total number of elements was 53 to the 4, which is a huge number. It took a lot of memory to store that tensor in that paper. Now we need to use as much n as possible, because when you go close to the critical points, say BKT, if you really want to locate the BKT phase transition, you really need to take n large because of various issues which I don't want to discuss here, right? So that is the initial tensor for XY model. The same story here as well. You compute the free energy, compute the first derivative of the free energy, compute the second derivative. This plot tells us is just showing you the values of temperature and different values of magnetic field, uh, which you can reproduce using the tensor network code, as we will see in a moment. So let's just go back and try to see how do we do XY model using these tensor networks, right? Okay. So since the basic structure of the course training and everything else is the same, what I'll just do is I'll write a new function. First of all, I'll write a new function which is, let's see if I have that. Okay, no. So yeah, let's just write down the same thing as this. It's going to be more complicated, but it's okay. So we can call this Z2D XY. It takes as input beta and also takes as input the magnetic field. Let's just construct something which I called beta, which is beta times H. Now for I in range minus dn, dn is something which I'll tell you what it is in a moment. Uh, np square root sp dot special. Sp dot special is for Bessel function dot iv. So this is going to give me a I with the index I and beta. Right. Then what do? I want to construct an out tensor using ncon. For example, I want to construct ij, ik, il as I wrote in the notes. So how do we do that? We just do that. We take 4 of these L. -1, -2, -3, -4. And the braces should be fine. And then I have to now again do the same thing. So this is left, this is right, this is up, this is down. And what do we do after that? Thing called the index, which is L plus R minus U minus D. And then you have out of plus dn. So out is has rank 4. So out L or U D is equal to multiplied by equal to sp special dot iv index b. Okay, so this is what we have. Now let me explain what this means. This part here is just this part which was under this in the square root in my notes. So if we go here, so this is this part, right? So all the L's are that this is constructed square root of I beta and 4 L's. And the second loop is where I construct index, which is L plus R minus U minus D. And that is just this. So note that this is IJKL and this is LRUD. So L plus U is R plus D. So if L plus R is U plus D, then this will pick up 1, and it will become equal to this object. Otherwise, it will go to 0. So you'll only have those elements non-zero where this condition is satisfied, right? So once we have this, we can just return the out. And then we can delete everything that was coming because of the easing model. And this is the initial tensor for 2D XY model, right? Okay, so now there's certain things which we need to define here because we have not done that. So dn should be defined here. Say I define this as 11 for the moment. H is say 0 0.0. So 2D xy beta h is 2 arguments taking 2 arguments. So I will just copy this line. And then I'll xy. So this is beta and h is h. So it's 0 0.0. And then everything is the same. You can try to run this and see if we land into some problems. Probably we will. Okay, it's because of ncon on line 68. Probably I'm missing a there. Uh, let's see. Oh no, probably I don't need this at all. Yep, let's see if this is okay, not okay. Okay, L is not defined, that's fine. We can define L as L of something up here. So L, let's define as NP zeros as some number which is say D. We should also define A as NP zeros D. D should be, let's see, D should be 20. Let's take this as 22. And this is going to be int D by 2 by 0. Okay, so let's see if this is still throwing a problem. Okay. Yeah, so let's see what is 69 I plus dn is this. Okay, okay, I think let's see. 22, okay, so minus 2011. I see 22. Yeah. Uh-huh. Yeah, okay, let's see. Maybe let me see if I have something which I've already worked out. Using, let's see if this something here which I'm missing. I can just copy that. Oh, okay, I have that code here actually. Okay, let's try to see if this one works. I'm still not sure why that was not working. Oh, okay. Maybe it's because of odd thing. It needs to be odd because you go from minus n to n, so you actually need 2n plus 1 entries. Let me just try that and see if that helps. Maybe, yeah, it does. Very good. Okay, so it's doing something. Maybe I should stop this because there are too many betas which I'm considering at the moment. I shouldn't do that because this is not as fast as the easing model, obviously. So let's just consider two values of beta and let's just reduce. Yeah, I think this should be fine. Okay, let's just do that. So it will take a couple of minutes to run. Till then, we can just go back and see what is going to happen. So for example, when H is 0, as I told you, you have a O2 symmetry, and that is picked up by this delta function, right? So we should be able to produce something like this if everything goes fine. We'll see what is the problem, why is it taking so much time. But the main goal to determine is to determine the critical temperature, like the BKT transition, which we want to determine what are the critical exponents, what is the critical temperature, and so on. So the way this works is we first compute the magnetization for this model by introducing some amount of a external magnetic field H, and then compute the susceptibility, and then take the zero field limit, and then we compute what BKT transition is. So if you do that, you reproduce fairly accurate results of the BKT transition uh, using tensor networks. So let's just go back to this code. So as you can see, it is doing for two values of these make no sense because there's just 2 points. So just look, let's look at the free energy. The free energy is for 0.38 and 0.39, uh, which is like, you can see that the zero limit is something like zero is up here. So this is around 1.2, uh, which is different here. I don't know why. But the basic idea is that you can compute the free energy exactly the same way like we did it for the easing model, right? And if you want to look at the paper, the code is also on GitHub repository, the code that can reproduce the results in the paper. So you can look at that GitHub repository for this. But the basic idea is that you can write down this F. Okay. So let's focus now on the determination of this TBKT. So right now, till now, I've told you how to compute things which are related to function. For example, the first derivative of the partition function, the second derivative, and so on. But now, if I want to compute the magnetization, how do I do that? Computing magnetization is little tricky. It's not very difficult, but we have to be careful and try to do uh, it carefully. The magnetization is also defined as the derivative of the free energy with respect to the field, external field, which can be represented like this: 1 by beta times d ln z by dh. Now, I told you that the initial tensor for the partition function was something like this, right? We saw that Tijkl was something like this. Now, if this eventually gives me ln z, right? This gives me ln z when I take the tensor trace and take a log of that. So if I want to calculate the magnetization, I actually want to compute the derivative of this function with respect to h. And that is what this T twiddle is. T twiddle is computing the derivative of T with respect to H. So if you compute the derivative of this object with respect to H, this piece is a constant because this doesn't depend on H. So you can just pull it outside. When you do a derivative of this term, the derivative of the Bessel function I nu x gives you I nu minus 1x plus I nu plus 1x divided by 2x or something, right? So now you see that this was I plus j minus k minus L. So this will become I plus j minus k minus L minus 1 and plus 1 by 2, right? So this is another fundamental tensor. This is known as impure tensor, and this is for magnetization. Now, the fundamental tensor is represented in this on this page by blue tensors. So these are fundamental tensors, all of these. When I want to compute the magnetization, I'll take the network, I'll take the tensor network and replace one of the tensors with an orange tensor. So orange tensor is the T twiddle, right? The T twiddle goes up here. And then what do I do to compute the magnetization? To compute the magnetization, I do the same set of contraction. So you can see that the indices are labeled here. So I goes with I, K goes with K, L goes with L, L prime goes with L, J goes with J, J prime goes with J prime, and then this gives me a number, right? So the numerator is a number here, the denominator is a number. If you divide that, you get the magnetization. And that is how we compute the magnetization. So computing any observable in this tensor network has to be done in this way. You take the network in the denominator. This is basically equivalent to saying that if I want to compute, say, expectation value of an observable, how do I do this? You do something like this, right? In path integral, you have this z here, normalization, and you insert a tensor. This is literally doing that, inserting the tensor O in that network and computing the expectation value of that tensor, right? So that is how we compute the magnetization. So for example, when we want to compute the magnetization using n-con, how are we going to do this? So we'll define m is equal to n-con of t twiddle t t t, and then we'll write things here with no negative integer, because this is going to be a scalar and this is going to be the same downstairs, just the fact that this is all going to be t. So that will compute the magnetization. So if you go and look in the GitHub code, uh, um, you'll find that this is being computed there, right? Now, the another thing is that we could have computed magnetization by taking a numerical derivative of f with respect to h. That is also possible. The reason we don't do this is that it is very prone to errors, and you have to do it for different values of h, right? If you want to calculate magnetization at some given value of h, you have to do it for different values of h and then take a numerical derivative. So it's more expensive and it is more prone to errors. So we use this method of inserting an impure tensor. Okay, so I have 15 minutes left, and I'll just briefly talk about this important thing, this entanglement entropy, which I mentioned yesterday, just because some of you were interested in this. So we have some time, and we can just try to do a small exercise in that. Okay, so let's talk about entanglement entropy. For example, this is basic quantum mechanics, which we're going to talk about now. So, for example, consider a state, some state, which describes two subsystems, right? So, for example, take a subsystem A. This is the configuration A and B. So you have some state psi AB, which is given by this phi A, phi B. Now, if the state is separable, that means once we trace out the B part, and that is given by trace B, trace subscript B of this wave function. So I remind you that the density matrix is just given by this, right? So when you trace over this state, you get rho A. And if rho A is equal to phi A like this, then rho A is known as a pure state, right? Pure state in the sense that this state will satisfy some properties like trace of rho A will be equal to trace of rho A square and so on. So if a state density matrix satisfies this property, then the density matrix corresponds to a pure state. So if this is like this, it's a pure state and the entropy is zero. This is a very important uh, idea that when the two subsystems are not entangled, then entropy is zero. If this is at zero temperature, then SA is also equal to SB and SB is also zero. So if we have a non-zero entropy, that signals that there's entanglement between A and B, right? And often we look into this, what we call as bipartite or von Neumann entropy of two system A and B. And we will do a very small example of this in which we'll actually see how to code this in the next 10 minutes. So we want to calculate the entanglement entropy and we'll see how that is possible using Python. Okay, so a brief description of what von Neumann entropy actually is. It was given in 1927. The entropy is defined as minus trace rho log rho. I am using a log lecture. People also you so this is log base 2 is common for quantum information people, but log natural log is more common for high energy people. But for this purposes lecture, I am just using log base 2. So this is the definition. As you know that the trace is the sum of the diagonal elements of this thing. So I can also write this as a sum of all the i's, rho I, which is the eigenvalue of this density matrix, log 2 rho I, right? Now, if we have a random ensemble, then what happens is all these rho i's are the same, and they are just equal to 1 by d. if rho is are the same and it's equal to 1 by d, where d is the dimension of the Hilbert space. So for example, we'll understand this once we go to the coding part of this. If all the rho i's are 1 by d, then 1 minus 1 by d log 1 by d times just gives me this, and d is nothing but 2 to the power p. So this is just giving me p. Now what is p? I didn't mention what is p. So suppose I have n spins, and then I divide that into two systems, right? This is system A, this is system B. So this is n spins. So take P equal to 3, n minus P equals to 4, right? So there were 7 spins, and I divide this into 3 spins and 4 spins. As I mentioned in the first lecture, the size of the Hilbert space for this is how much? 2 to the P. And 2 to the P is what I refer to as D, right? So D is 2 to the P, and this gives me P. You can read more about this on very nice notes by Preskill on page 15 of chapter 5 if you're interested. Okay, so I think we should go to coding this. This is a very interesting coding exercise. So you don't need to worry about or debug anything. I'll just open that, and I'll open this file which is called EE computation. Okay, so what this code generates a random state of n qubits. So n qubits is just n spin half objects, for example, for purposes of this exercise. So spin up or spin down, n of them. So the size of the Hilbert space is 2 to the n, as we discussed at the start of the first lecture. And then we'll compute a reduced density matrix of first p qubits, and we'll see that the entanglement entropy of the first p qubits is exactly equal to p, right? And that is because entanglement entropy is equal to p because it's a random state, random ensemble, and maximally entangled state saturates the value of s, which is p. So the maximum value of s for this case can be p, and it will be p if the state uh, is maximally entangled. So we'll see how that comes up in this exercise. So we import all the usual stuff here. Let's say we take n equal to 24 spins, but we divide it into 5 spins and 19 spins. So psi will be 2 to the power n. We normalize psi by the norm of this so that this becomes a unit. The density matrix is normalized, and then we reshape psi in 2 to the p and 2 to the n minus p. So this is uh, making it a and b subsystems, right? And then I compute the rho, which is just going to be dot of a times transpose of a conjugate, right? So this is constructing rho, because for rho we have a bra and a ket. So they're related by transpose conjugate. So this is how we construct this rho. And then we compute the entanglement entropy of this rho. How do we do that? It's like how we did in the tensor network algorithms. You do this linear algebra I routine. It computes the eigenvalues and the eigenvectors. You start with entanglement entropy equal to 0. You go from 0 to the length of u. So for example, you have to go over all the u's possible, right? So we go over all the u's. So this shape is this length of the chi is just the length of u. And if the eigenvalue is greater than 0, I don't want 0 because then the log 0 will not be defined. So I want to only eigenvalues greater than 0, and then compute the entanglement entropy by doing this. This is rho. This is sum over rho I log rho I, as we mentioned, with a negative sign, right? And this will return EE, right? This becomes costly if P is greater than 7. So it will exit if that is the case. And now we'll compute this and see what is the entanglement entropy, for example, say when P is equal to 5. We know from our analytical calculation that when P is equal to 5, the entanglement entropy should be equal to 5. And we'll indeed see if that is the case for this thing. So let's just run this. Okay, so 4.999. So this is 5. So this tells me that this is exactly what is happening. So this is how you compute the entanglement entropy for a given state or so on, right? So this I can increase P. It will always be equal to P. Whatever P I take, for example, it will always be P, because this is a random psi we generated. This is a random psi. So this is like a random ensemble, and random ensemble is all the eigenvalues are equally probable, and it's maximally entangled, and it saturates a value of S, which is log of the dimension of the Hilbert space, which is uh, just equal to P in this case. So for example, P equal to 7 gives me 7, right? So this is one exercise where we compute the eigenvalue of the first P qubits, uh, where the whole system is formed of n qubits. This is what I wanted to discuss. Uh, Yeah, I think that's all I have to say for this these two lectures. If you have any question, you can write me an email. Otherwise, I'll put most of these things in the Dropbox folder, and you can look at the GitHub repository if interested. Yeah, thank you.
Great. Thank you for the great talk.
Okay, I think.